Good morning, everyone. First of all, today I will talk about the assimilation and the application of this methodology to the smart management of oxygen supply. Let me first of all thank Francesca and Mauro from EPC that are organizing that are supporting us in organizing this summer school. And they are doing a great job. Then I would like also to thank Joe and Fergal for the presentation, for the very good presentation. They already underlined some of they already highlight some of the challenges we faced trying to implement precision aquaculture. And it will be very useful in order to better follow my presentation. And so you will see I will repeat at the beginning some of the elements, in particular Joao and Roberto in his introduction already presented, but I think it's useful to fix some elements about modeling. So who I am, first of all, I'm an electrical engineer. I graduated in France, inside de Lyon. I had then several experiences as a software engineer and also let's say, technical project manager in several fields like aerospace or manufacturing. And I finally became a data scientist for aquaculture in 2016. And I'm within the GAIN project from April 2019, working mainly on data processing and mainly for case study in Italy, in Rainbow Trout farm that I will present further soon. Just a few words about my profile. I think it's very important for you to understand that we are doing a job in which sometimes you need some skills that are a bit far from that seems far from what you study maybe, or from ecology, or for example, I bring many skills of software programming in this project, and I think it was very useful for all. It was also useful for me to learn different things, but it was also maybe useful for the project. So don't underestimate some profile that maybe are a bit different from what you're used to see, but that can be very useful to you. So what I will present you, what I will talk about today, I will talk about, first of all, about some elements of modeling, and especially the GAIN approach we try to follow in this case study. I will talk about the dissolved oxygen model we set up and implemented for the Westway farm. I will shortly and briefly present the data assimilation methodology, trying to make it the most comprehensible as possible. And then I will try to illustrate how we combine the data assimilation and the oxygen model, and in order to try to better to improve the oxygen management within the farm we are working with. And I will finish with some examples of potential applications. So to go back to the modeling approach, some principles. So Joe already explained it very well. I just want to remind some few elements. So very simply, you can see that you have a real process you want to model. First of all, you have to define what is your system within this process. Sure, you will have to understand what are the inputs and the outputs. You will, if you want to go further, you can introduce a layer of measurements. Measurement, for example, the inputs and the outputs. Once you have the inputs and the outputs, you can apply the model using mathematical equation. So, and the model mathematical equation that you think that represent the system, and then you can compare what you measured with what are your provision with the goodness of fit indicators. This is more or less, very briefly, the way the path we followed in this case study. Few words also about the precision fish farming. So as Roberto already told you, it's a paradigm that comes from agriculture, from precision livestock farming. I would add that it is made possible thanks to two elements that regard the hardware and the software. So if we talk about a bit with a more engineering point of view, so from one side you've got the availability of low-cost sensors, the better availability of web access almost everywhere. You've got the Internet of Things that connects both sensors and web access. And also, we know that during the last decades, we had a rise in the processing capacity. Regarding the software, we now have a very data science that is taking many that is always much importance. You also have the rise of user-friendly languages like JavaScript, and then more recently Python and R are becoming very important. And I said user-friendly, which means that maybe they are more. It's more easy now to try to develop some routines to try to make some processing of your data. And I think it helps in increasing the importance of data science and its use in agriculture and now in aquaculture. The precision fish farming approach, so the aims are, of course, to improve the accuracy and the precision and the repeatability in farming operations. The idea is also to facilitate a more autonomous and continuous biomass monitoring. I would say that the challenge, maybe more challenging, is to provide a more reliable decision support. So that means you don't more than only monitoring what is going on. You need to find a way to provide the farmer with indicators or with methodology to help him taking decision. And of course, the idea was also to reduce the dependency on manual labor and to improve the staff safety. So if we go back to our modeling approach, so precision fish farming is talking about some steps that are very important. So you've got your system, you've got inputs, outputs, and the first step is to observe your system. And it's the first step of precision fish farming. Then you need to interpret your system. So what you observed, so you need a model to interpret it. Then from the model and the observation you made, you can decide, you can take decision. For example, having to have a control strategy of your process, and then you have to act. So once you decided the control strategy, you can implement some action in order to control the process. So this is more or less the precision fish farming steps that are very, very important to understand. If we talk about modeling approach, we need to be clear about what kind of model are we talking about. Fergal and Joe already talked about this, to you about this. So just a short remind, two kind of model. Let's say physical model that are methodology more model oriented. You've got mathematical equation, of course, mathematical equation that try to describe the physical process. And of course, as Joe already explained, you will have to make some hypotheses that regard the various processes at stakes and at stake, and the relative importances with regard to the dynamics of the outputs. So you will have to simplify and to make some choices. Then you also have a data-driven model that Fegel already presented you. Again, some mathematical equations, but the model tried to find some relation between inputs and outputs using a statistical approach, and with no specific links to the physical process, even if you need to have a bit of understanding of what's going on, but above all to interpret the results. But you don't have a description of the physical process, and here you have to make some choice among the methods, and also to understand what is the complexity of what you want to implement as a model. In this presentation, I won't speak about the data-driven model. I will focus on the physical model, so the dissolved oxygen model we used was a physical model, and we had some data assimilation approach, which is maybe a kind of compromise between both models, but I will talk about it further. What we studied in this case study, so we focused on a rainbow trout farm. So we are talking about freshwater aquaculture. So freshwater aquaculture in Europe is quite important. I reported here the importance of freshwater aquaculture in terms of total sales volumes, following the various countries, and you see that Italy is the first producer in terms of volumes. The species, mainly rainbow trout and common carp, are two case studies of the game project. What about the rainbow trout production in Italy? Well, rainbow trout in Italy has a kind, let's say, of a recent story with a constant increase from the 60s and a peak in 1997 in production. And over the last decade, it's quite stable around 40,000 tons produced of rainbow trout. The production is mainly located in northern Italy, because you have more available water providing from the Alps Mountain. And the type of companies and products, most companies are medium, small size companies. There are also some bigger actors in the field, but many are small companies, and they are often family run. There is a long history of family companies that try to and then manage to implement freshwater aquaculture, and they are going on in this northern part of Italy. Two kind of cells. The fish that are less than 500 grams are sold entire, let's say gutted and hung, and the larger fish are converted into processed products like fillets, hamburger skewers. And in the short farm we work with, they were produced both kind of products. So the trout farm we worked with the Fratelli Leonardi farm. It's a family business, so very typical from this activity. It has around 10 employees, and it has 3 different production sites. We worked mainly in the site of Preore. This farm has 7 raceways or flow-through systems. So to be clear, it means that the water comes from the river. It passes through the raceway where the fish are grown, and then it go back again into the river. The raceways are 200 meters long, 8 meters wide, and 0.8 meter deep. The water is coming, then the river, the water is coming from is named the Saka River, and it's quite important in the area because there are several several farms that are using this water. A schema of the farm. So as I said before, you've got the water that coming from the river. You've got also in one of the raceway, the first one, you've got some groundwater, but it's not the main part of the water supply with the recirculation. And first thing you see that is that they use an oxygen supply. So every raceway is supplied in liquid oxygen in order to warrant a certain level of dissolved oxygen concentration for the fish. And this is made through, because there is plenty of system that's allowed to make oxygenation of water, also aeration. We'll see further, we'll see later. And this oxygen supply is made through a low head oxygenator, which which was designed by the farmer, and that's allowed to dissolve the oxygen, the liquid oxygen, within the water that come into the raceway. Today, in terms of sensors, the farmer is using some sensors in the middle of the raceway, also at the end. I didn't represent it in it, also at the end of the raceway. And it had some valves. You can see on the left side, on the green left side, some valves that allow to supply the oxygen to the raceway. What about DO concentration in the water? So you got two kind of problems depending on where you are taking the water. If water is from ground, you need to supply many oxygen because it's lowly oxygenated. So it's the big concern with the water from ground. On the other hand, the water from ground is quite stable in terms of temperature. So depending on what you want to do, you need and what's available where you're working, you have to face these challenges. The water from the streams is often, it can present high concentration in oxygen, but it can also present high variation following the seasons. So it's and also the temperatures can be very different depending on the season. So you have to be very careful, very aware of these variations. How can you, if we think about how can we improve the oxygen concentration in the water, you have many different systems that allow to do it. I would briefly say that we can think in terms of aeration, which are mechanical action, like moving water in order to use the oxygen of the atmosphere and to enrich the water. Or you've got also the oxygenation, which is different and which aims to use liquid oxygen, so big tanks or tanks of liquid oxygens that you will supply, and you have to find an efficient way to supply this liquid oxygen to the water. So going to our case study, and how do we frame our problem? So we define the system first, and our system was the DO concentration within the raceway. So if we think in terms of inputs and outputs, which is a simple way that's a very interesting way to see the things. You've got the water as input, the oxygen supply, you've got the biomass, and you've got also the exchanges with the atmosphere. And the output was the dissolved the oxygen that go out from the raceway with the water. So we try to describe this physical process. we used a mass balance of dissolved oxygen. We make a list of contributors, and we build up a differential equation. We made some hypotheses, of course. It's crucial to the modeling activity. So the two main hypotheses were we have the three main hypotheses. Sorry, we have a complete mixing of water within the raceway. What does it mean? It means that the biomass, we support the biomass, the fishes are uniformly distributed within the raceway, which of course is not always the case, but it's an assumption. And we think about the raceway as a point. I mean, we didn't, in the first approach, we didn't model some gradient concentration within the raceway. It means we think that the dissolved oxygen concentration is the same in every point of the raceway. That's it. Then we decide not to take into account the primary production because the water residence time, 48 minutes, if I don't even mind, means a good replacement. So no stagnation of the water within the raceway, and also because we estimate that the water from the Saka River was kind of clear water with no particular influence on the primary production. And then we also decided to take into account the exchange with the atmosphere through a reaeration process. The result is this differential equation. So don't be afraid, it's quite simple. You've got in blue the positive contributor, and in red the negative contributor to the mass balance of oxygen. So again, the water that comes in is a positive contributor. The water that goes out is a negative contributor. The oxygen supply provided by the farmer is a positive contributor. The reaeration can be either positive or negative depending on the respective concentration of the respective pressure partial pressure of oxygen in the air, in the water. And of course, what could be of huge interest for us is the fish respiration, which is a negative contributor. We then implemented an experimental precision fish farming system. So if we think about a raceway, again with the water in, the water out, and the oxygen supply, what we did was to add two kind of probes, two probes, let's say, in the inlet and in the outlet, two kind of oxygen probes, in order to understand what is the concentration of the water that comes from the Saka River before the oxygenation process. And also to understand what the concentration at the outlets, in the outlets of the raceway. And then we also used a biomass monitoring system, which name is Biomass Daily. I will maybe further present in the next station about it. That's allowed to. It's a system that was used for the salmon cages, and that we tested in the raceway trout situation, which is kind of different, but it gives us some real interesting results. So we focus, of course, on the fish respiration, and we try to make a calibration of the fish respiration. So we already had an idea of what is the trout respiration rate from the literature, but the rates that are reported in the literature are mainly measured under artificial conditions, and it's quite hard to find some estimation in real condition. There are some but we thought it was very pertinent to try to build about a precision fish farming system, which means real conditions and to try to make an estimation of this fish respiration rate. We made a quite simple calibration process, which is a very common thing that is made when we work with modeling activities. We try to find the respiration rate, Rn, that minimize a goodness of fit function. So we run the model, we see what is the time series of the output, of the forecast of the oxygen in the output, and then as we made some measurements of the outputs, we compare our forecast with the measurements, and we try to let's say to tune the fish respiration rate in order to have the forecast which is the best which is the best estimation of what we observed. We also try to create some synthetic time series using the sampled one in order to have an idea of the parameter, it's the respiration rate dispersion. In terms of results, so this is a simple dissolved oxygen model. You have the forecast and the measurements, the forecast in blue and the measurements in red. We've got almost 1 month period with hourly data. You can see that the model function is quite good to forecast the value in the output during the first half of the month. And you can see that on the second half of the month, the measurement is there is a higher variability in the observed dissolved oxygen concentration, and the model is less efficient in predicting the oxygen concentration. It's not so bad, I would tend to say, but clearly it has more difficulties to reproduce the real measurements. If you want to go further, I built up a web application on this now model, which is available at this link. If we had a quick look, if I managed to go to my browser, okay. Let's try to refresh. If you want to make some tests, it could be useful to understand how the model is representing the real process. Okay, so I already set an input data set, and you can choose between two representations of the respiration rate, constant or sinusoidal. I won't speak about sinusoidal, but briefly, it's to represent the daily intraday variation of the respiration rate, and you have many parameters about the raceway, the oxygen supply. You can choose, and if you run, you will see your simulation and the measurements. So for example, if you try to modify the oxygen supply, let's say you double the oxygen supply, you will see the difference because the oxygen at the output you are forecasting is of course higher because you supplied more oxygen. So just for you, if you want to make some kind of a short test. So this was let's say the simple modeling of the dissolved oxygen. What we did after that was to try to think in terms of data. I mean, we had a model, we had some data, but we tried to think about a good way to better use the data that was available, and our choice was to use the data assimilation methodology, which is well known, which very different methods in data assimilation, but it's a paradigm very well known in data processing. And mainly it consists in combining the model prediction, so what I showed you, and the observation to improve the estimation of the state of the model, and to try to make the model, the parameter of the model not so static. To use the data you are acquiring, every new data, you will use it as to improve your model and to improve the state of your model. So it allows a more reliable forecast, because all along your sample campaign, for example, you will be able to use the data already available to try to improve the model, and then to try to improve the next forecast. So you will improve your forecast and to make it more reliable, which was with more close to what is really going on. So it's a kind of model-oriented method, but also data-driven method. Means you made a kind of a data fusion between what you are observing and what you are predicting. So you use the model and the measurement. Where does it come from? Well, it comes from it's an approach that was designed by mathematics and also engineers. It was think in meteorology to build a reliable weather forecast, but it was also design. It was the field in which it became very important is the space in the 60s. It is used today. It is used in several fields like oceanography, meteorology, space, and ecology, and there are many different methods in data assimilation. So if we try to understand what does it mean for our process, data assimilation, so we can, if we think about the 4 steps of precision fish farming, if we concentrate on this part, which was the decide and interpret, instead of going there, let's say directly to the decide step, you can think that your interpret loop is longer. You will use the outputs of your model and the outputs of the system to feed a data assimilation algorithm that will allow you to improve your model and to improve your prediction. So then you can go to the decide, to the control, for example, in this case, step with so you will mainly make your interpret phase more rich and more pertinent. What kind of data assimilation method do we use? We use the Kalman filter. So a bit of history about the Kalman filter, which was developed in the 60s by mathematicians and engineers, as I said. And one of them was Rudolf Kalman, and they gave the name to the filter. We talk about a filter. It means an algorithm, and the first that understand that this filter can be useful to let's say a concrete and let's say important application was the NASA engineer Stanley Schmidt, and it understand that it could be applied to the Apollo trajectory, because they had a trajectory problem, and he realized that it can be implemented, the Kalman filter, within the navigation computer of Apollo, try to better estimate the trajectory of the spacecraft while it's going on. And today it's still in use in aerospace. For example, in the RM5, which is the main European launcher in the guidance and navigation control system, and also for some application of what is called the rendezvous or docking. For example, when some spacecraft are arriving in front of the International Space Station, they have to know very precisely what is our position and the relative position of the space station. to allow the docking. And the Kalman filter is still very useful for that kind of thing. Why did we choose it? We choose it because it's a proven methodology, one of the most widely data assimilation methods. And it's quite, we choose it also because of its versatility. The Kalman filter has different formulations that allow to deal with different types of problems, like linear, non-linear, continuous, or discrete. And it was already applied in ecology, and we thought it could be very interesting to apply it to our problem. Its principle more in details. So if you think about your model that has some parameters, now Kalman filter allows you to say, I want some parameters of my model to be treated as stochastic variables. So you have some parameters that, for example, in our case, that are non-observable variables that can become, in the approach of the filter, that can become variables in time. So they are, let's say, included among the state vector, which is the vector of the variables. And then the Kalman filter is using as every data assimilation method is using every new observation that is available to correct also, of course, the forecast, but also the parameters itself, and also then the non-observable parameters you decided to be variables. So it's very useful. The consequences, as I already said, is that you improve your forecast and you have some parameters that are changing in time. Going back to our disordered oxygen model, what does it mean applying the Kalman filter? So if you look at the fish respiration, the fish respiration equation we used, we decided to represent the fish respiration. Within the fish respiration, we decided to model the influence of the temperature and also the weight of the individual of the fish. N is the number of the fish in the raceway. So the two main drivers are temperature and weight. So this means we decided not to take into account other kind of influence on respiration rate of the fish. For example, the first thing you could think about is that we didn't take into account the influence of the amount of feed that is supplied to the fish. Of course, if a fish has more feed to assimilate, surely the respiration rate will be higher. But it was a choice. It's a good example of how you make choice in modeling activity. And then we decided to use this fish respiration, this RM, as a parameter and normal as parameter in the filter, let's say as a variable. So the filter steps for every new observation. So every time we had a new disordered oxygen value available, what did we do? We forecasted the corresponding value from our model using the last forecast, and so this is the propagation, let's say, and this forecast was compared with the new available day observation. The difference between these two was, let's say, weighted. There is a specific terms in the Kalman filter, which is the gain that allows to weight the difference between observation and forecast. And the respiration rate was then adjusted according to this weighted difference. So this is more or less the three-step of the Kalman filter. To try to represent it as a schema, so you've got as inputs, you've got the biomass, the disordered oxygen and the temperature, and the oxygen supply you are supplying to the raceway. you have, they are all inputs to a dynamic model. The dynamic model, the simple model, let's say, allow to build some forecast of the state, which means forecast of the dissolved oxygen and also the respiration rate. But then you have also some measurement of the dissolved oxygen. So you can compare measurement and forecast. And you go to the Kalman filter that allow to improve the knowledge of the system, and you can improve your dynamic model. Doing so, at every step, because it's a sequential process, at every step you also have an estimation of the respiration rate. So it's not only improving and making and improving the forecast of the dissolved oxygen, it's also trying to have an estimation of the respiration rate. The result, so in terms of dissolved oxygen, this is the result. So we have a better performance, the Kalman filter forecast with respect to the simpler model in terms of goodness of fit. And so you can see in particular that it's quite a very good forecastability during the first part of the month. And if you remember, we had some concern in the second part of the month with the simple model, and you can see that the performance is much better in the second part of the month. It's not. It could be maybe better, but if you consider the high variability of the measurements, the filter is able to make a very good forecast of the dissolved oxygen. If we have a look at the respiration rate, so instead of having, as I said before, a fixed respiration rate, we fix it at the beginning, and then we use every new measurements and the filter algorithm to try to adjust the respiration rate in front of every new measurement. So if you represent, and it is the blue curve, the blue line, if you represent the respiration rate, you can see that you have some clear daily oscillations due to circadian rhythm. And it's quite interesting to see that the phenomenon that is described in literature is reproduced by the filter. It means that it could be it's very useful. And the second thing you can see is that if you look at the brown curve, the brown line, which is the feed ration in with respect to the average weight of the fish, you can see the influence of the feed ration on the respiration rate. So as I said before, for example, these two, and I talked before about the feed regime, we choose not to take them into account in the equation of the respiration rate, and in order to simplify our model. But if you use this kind of method, allows you to take into account these processes, and they are able to show you that there is this influence, and of course it means the method allows to manage to deal with this kind of processes, even if they are not modeled by your equation. So it's quite interesting. 3 examples of applications. Of course, the first thing you can do with this kind of method, you can in dissolved oxygen, you can think about a smart control of dissolved oxygen supply, because you have more reliable forecast of dissolved oxygen concentration, and then you can think about today the oxygen supply is fixed by the farmer, and it remains the same for a long period. It's fixed based on his menu and based on his experience. But you can try to use our estimation to build a control, a dynamic control. So hour after hour, you can try to fix a new oxygen supply in order to better stick what is the real need of the fishes in the raceway. And this is, I think, a very interesting part. The benefits, of course, are cost saving because liquid oxygen is one of the main costs of the feeding and labor. And of course, because you have a better monitoring, a better control of the animal welfare, because you can prevent some quick changes in this oxygen level, changes that can be very, very problematic, very harmful for the fish. The second application we can think about is that, of course, you have an estimation of what's going on in the effluent. So you can think about an early warning effluent because the water is going back to the river. So you can monitor what is the quality, the water quality, the quality of the water I'm giving back to the river, and you can then preserve the natural ecosystem of the river. So it could be very useful, and you can also think to apply this methodology not only to oxygen but to other parameters, because as you saw, the model is quite simple, and you can think about other parameters that are maybe more pertinent for the water quality in the effluent. And finally, you can think about quality control, because you made a comparison between what you forecast and what you measure. And you can maybe try to identify some anomalous situation, because in all this you are thinking that what your sensors are telling you, and every sensor can have some failures, and you can detect some unexpected sudden changes that can correspond to potential concern with the system, and you can raise, for example, some alarms to the farmer, some alerts to the farmer in order to prevent from huge consequences. For example, I simulated a failure in the oxygen supply. So I used the model, the simple model, to build let's say a time series of what could be the oxygen in the output if you have a failure in the oxygen supply. So in the 7th of July, and what you can see, one parameter of the filter is the innovation. So how much he's correcting the forecast he made, and you can see that you have a big peak in the estimation, which corresponds to the failure in the oxygen supply that maybe was not detected by the let's say the electro valve or the device itself. But this methodology allows you to show that something is going wrong, and it could be very useful also in this kind of situation. Quality control is very important, because you can always trust in the information you retrieve from the sensors, and you have to think about it when you try to implement real system. So as a conclusion, first conclusion for the engineer or for the scientist, if we think about these data assimilation benefits, let's think about online, I mean real-time data assimilation. So it allows you to increase the forecast capacity of simple models. So maybe you don't have to use a very complex model. You can use simple model and data assimilation methods in order to have a good representation of the physical process. Of course, it's opening the way to smarter control, because you use this estimation to try to better control, to try to better build real-time control of your process. And also you can try to detect the anomaly within your system. These are main benefits in the real time if you think about a real-time process. Then if you think about let's say an offline process, once you if you want to make an exploitation of the results you already observed, you already obtained. Well, you can improve the description and there's the listening of the process itself. In this case, if you have a look at the fish respiration, that is supplied, that is the output of one of the output of the filter, you can see that well, there is a big importance of the feeding regime. And for the scientists or for the engineers, it could be very interesting because the next step could be a decision about the model. Must I take into account the influence of the feeding regime within my model? Could it be interesting or not? Or this is the approach you could think about. For the farmer, well, the data assimilation could be very useful in order to supply the pertinent oxygen quantity at every moment, and it can be very, very, very interesting instead of having to set a constant rate of oxygen supply for I don't know, the whole week or the whole month based on his experience. The failures that can be detected to anticipate the potential damages to the biomass could be also very interesting to detect, for example, some failures in the probes that gives you the sensation that you've got the situation under control, and maybe it's not the case. And also the water quality in the effluent could be very interesting for the farmer to avoid negative consequences on downstream ecosystem. You know that the rules are always more important for the aquaculture farms, and it's a good point. But we have to, I think, we have to help farmers to give them some indicators, some tools in order to be better in the situation of being able to respect the regulation that they face. And surely one goal of the precision aquaculture is this to help the farmer to better face these challenges. So basically, for the farmer, it means cost saving in any case, and it's very important to keep in mind in this aspect. So that's all for me.
Thank you.